Thank you, Professor Mukhopadhyay, for the interesting talk. We have had several questions coming in from the audience, so I will start with the questions right away. So the first question, Professor Mukhopadhyay, is from a participant who wants to ask about the fabrication strategy of electrodes. And as a synthetic strategy, how do we control the distance of NaO? X is the other element bond in the electrode material.
Okay, thanks for the question. So the electrode preparation is, I mean, for a typical electrode which goes in a real cell, battery cell. I'm not talking of miniature cells or thin film based electrodes here. So one has the active material for like as I talked about in my talk, it was layered sodium transition metal oxide. That is the active material. Now for preparing an electrode, one has to mix the active material with some binder and some conducting additive like carbon black or a little bit of carbon fiber, and then prepare a nice homogeneous slurry with the right viscosity and then coat it on a current collector. Now, this slurry is typically made using a non-aqueous medium like NMP, N-methyl pyrrolidone, which is very toxic and hazardous. So the point is, if we can replace the usage of NMP with usage of water and associated by, and a water-based binder, that can make the electrode preparation much more health and environment friendly and also reduce the cost by say about 15%. So that's one. Now the sodium oxygen and oxygen transition metal oxide bond. So let me go back to the slide. Okay. Can I not share the slide now?
Yes, absolutely. So Aparna, could uh, Professor Mukhopadhyay share the slide?
It's easier to explain that way. Thank you. Right. Okay. Let me go to this structure first. Yeah. So the beauty of this layered transition metal oxides is that uh, the, the oxygen ion is connected on one side to the alkali metal ion, in this case the sodium ion, and on the other side to the transition metal ion. So now this is a predominantly ionic bond. Okay, now let me go back to the next slide which I was using. So while this is predominantly ionic bond, so as such not much can be done to this, but then this is a iono-covalent bond. So now if we can increase or decrease the covalency of this bond, we can decrease or increase the effective negative charge on the oxygen ion. And by playing with the effective negative charge on the oxygen ion, the length and the strength of the ionic bond, which is sodium oxygen, can be tuned. So the length of this bond depends on the covalency of this bond. Of course, the ionic radius will also come into the picture. But given if the ionic radius of this is the same, then if this is more electronegative, then the covalency increases and the bond becomes a little short, and so on. And if the effective negative charge on the oxygen ion goes down due to the enhanced covalency, then this bond will become longer. So that is how we can manipulate or we can tune the length of the transition metal oxygen bond and the sodium oxygen.
Okay.
I hope I answered the question.
Yes, absolutely. Thank you, Professor Mukhopadhyay. So because you talked about the use of NMP, so I take up another question which is on NMP, where the participant is asking about how to overcome the use of NMP, like you said. And because we are talking about the sustainability of the lithium-ion battery process in general, is there any other aspect, for example, flammability, whenever we talk about safety of sodium-ion batteries and compare it with lithium-ion batteries?
Okay, fine. So first of all, in the usage of NMP can be done away with if the active material is stable in water. In that case, we can use water as the medium for electrode preparation, and we don't need NMP. And usually the anode side is water stable, the hard carbon or graphitic carbon. And so as so like even now, most of the the anode electrodes are made using water-based slurry. People are not trying to get away with NMP for the anode side. Now the cathode side is a challenge, because even in the lithium ion system, when we are going to high nickel containing lithium NMCs, so they are also hygroscopic, so they are not stable in water. So one is forced to use NMP. But if we can render them water stable, just like I was talking about for this sodium transistor metal oxide, if we can render them water stable, then we can prepare the slurry using water, and we won't be needing NMP, which is good to do away with. So that is the first part of the question. Now, whether it's usage of NMP or water, it is dried off before the cell fabrication. So, that is not likely to have impact on the safety aspects when it comes to the cell operation.
Mhm.
Of course, NMP itself is hazardous. So while electrode preparation, it is not safe when NMP is used. But when it comes to the cell usage, once the medium is dried off properly, that uh, that is least likely to have an impact on the safety while operation. Now, the safety while operation is decided by how good the upper and the lower voltage cutoffs are tuned, and to go with the cathode anode capacity ratio. Now, during the operation, one does not want the lithium plating or the sodium plating to take place on the anode side, and the oxygen or the gaseous evolution to take place on the cathode side. So if these can be avoided, then a lot of improvement can be done in the safety aspect, or it should not be unsafe. So now the moment something wrong happens, as I told, the temperature can shoot up, and especially if there is a plating and a short circuit because of the dendrite formation penetration, and if the temperature shoots up, we use organic electrolytes which are flammable. So then there can be a fire hazard and a safety hazard associated with it.
True. Yeah. Thank you, Professor Mukhopadhyay, for the detailed answer to that. So, just one question as a follow-up to that, that a participant has asked is, does porosity of any of the structures affect the electrochemical performance?
Absolutely. So porosity is not a good thing to have in a battery electrode material. So that is because in a battery electrode material, one does not want too high a specific surface area, because while on one hand, having a high specific surface area can have a good impact on the rate capability, uh, but it will have a detrimental effect due to the excessive occurrence of the irreversible reactions, which are highly detrimental. So one does not want the irreversible reactions to take place at the electrode electrolyte interface, and so one does not want a very high specific surface area. So having a porosity in a battery electrode material is not really good. And in fact, the battery electrode materials, the particles are not nanoscaled in size. So they are micron scaled in size, unlike in supercapacitor. In the supercapacitor, we would like to use nanoscale materials with lot of mesoporosity and even microporosity to enhance the specific surface area. But that is detrimental to a battery performance, because it can lead to exacerbated irreversible reactions which are bad, which can increase the cell impedance. It can reduce the reversible capacity, and it can lead to progressive capacity fade. So it is not a good idea to use porous electrode materials in a nutshell.
Yeah. Uh, Thank you, Professor Mukhopadhyay. So I'll take the next question, which is on the practical application and is kind of a comparison between lithium and sodium-ion battery again. So the practical application of sodium-ion battery systems is limited due to operating voltage limitations. So if you can share your insights on how cathode or anode design can actually alleviate this problem.
Yeah. So the cathode materials in sodium-ion battery, for the same structure, they are expected to have a lower. So suppose everything else is the same, the structure is the same, the composition is the same. A hypothetical case, comparing lithium ion with sodium ion. So the ones with sodium ions, they are expected to have a lower operating potential, and that goes with the free energy change that will take place when the sodium is taken out and the sodium is put back in, and the free energy change will affect the influence the operating potential as per the Nernst equation. So that is an intrinsic limitation. But yes, one can design cathode materials which can have a higher operating potential. It is possible to design, and one can. So one of the way out is probably trying to have oxygen redox and have a reversible and safe oxygen redox, trying to render it feasible for the layered sodium transition metal oxides, which thankfully is much more stable if one compares it with the lithium transition metal oxides. But yes, having said that, as of now, the oxygen redox is not yet stable for a practical usage, and a lot more understanding of and lot more work needs to be done to render it stable. But if oxygen redox is rendered stable and suitable for practical usage, maybe in the future, in the near future, if I want to put it that way, then the capacity of the cathode materials can increase, and so can the operating potential, because oxygen redox takes place at a relatively higher potential compared to the cation redox. So that is the way in which the capacity as well as the operating potential of sodium ion battery system can be increased, but lot more work needs to be done on this respect, and that is why researchers have to work on this. Yeah.
Yeah. Thank you, Professor Mukhopadhyay. So, uh, like you discussed your research on the influence of charge to radius ratio on the rate capability of um, sodium ion batteries. So, is it only the charge to radius ratio, or is there any other factor that could be of vital role?
Okay, so charge to size ratio is just one factor. So the reason that was an influencing factor for the materials that we talked about, because everything else was kept constant, and by enhancing the charge to size ratio, for example, by replacing a little bit of titanium with silicon, the interslab spacing could be enlarged. If the interslab spacing could be enlarged, the sodium transport could become more facile, and the sodium diffusivity increased, as I had shown based on a plot with respect to the sodium ion diffusivity, and so the rate capability increased. But rate capability will depend on a host of factors in addition to the bulk sodium transport. Of course, the bulk sodium diffusivity is one of the major factors, but in addition to that, the resistances, which also include how the electrode electrolyte interface behaves, the ACI or the CEI layer that forms, and the particle size. So all these things will have a big role to play when it comes to determining the exact rate capability.
Okay.
While yes, the intrinsic sodium transport is probably a major factor, and that can be influenced by, in the layer transition metal oxide structure, that can be modified by modifying the interslab space.
All right. Thank you, Professor Mukhopadhyay. So, I guess the audience have shown their enthusiasm. There are too many questions, so just for the sake of time, we'll pick up the last couple of questions, maybe if that is fine. So, uh,
I have a lot of time in my hands, so I am
okay,
okay. It depends
okay,
on the thing.
yeah, yeah. Thank you, Professor Mukhopadhyay. So, the next question is a very specific one. Could you please share your thoughts on distinguishing octahedral and prismatic sodium ion environments using solid state NMR? Yeah.
Okay, okay. So so solid state NMR is a very specific technique, and I am not a person who should be talking about solid state NMR, because if I try to say that, I may go wrong. The best person, one of the best person, is Professor Claire Gray, who is an expert in solid state NMR. So I will refrain from talking about interpretations based on solid state NMR. I can go wrong in that.
Okay. Yeah.
So sorry about that, but I am not the right person for that.
Yeah, absolutely. Thank you so much. So, the next question, Professor Mukhopadhyay, is the comparison of, okay, I think this is like very general. So, is there a similar oxygen loss at higher voltage in the case of sodium transition metal oxides, similar to nickel rich NMC?
Yeah, that is very close to my heart. So okay, so it depends on the on the how where the transition metal bands are placed with respect to the oxygen 2p band. Right. So now, if there is an overlap between the transition metal band and the oxygen 2p band, like it happens when there is some cobalt in the layered transition metal oxides, like lithium cobalt oxide or NMCs, there can be something which is known as a lattice oxygen evolution, which is actually very bad, because then it is competing with the transition metal redox when it comes to the capacity. So we don't gain any extra capacity, rather there is oxygen loss, and that leads to a structural degradation. So since we are not using something like cobalt in the layer transition metal oxide, this aspect can be avoided. But having said that, when we enter the regime of oxygen redox, once oxygen redox is not controlled, it can lead to formation of molecular oxygen, and that can lead to oxygen loss, which is again equally harmful. So yes, the answer is there is a possibility of oxygen loss even in with this layered sodium transition metal oxide, and that is when the oxygen redox gets invoked, and if it is not controlled, molecular oxygen can form at certain stage, and that can lead to oxygen loss, and which is something which needs to be avoided by proper understanding and control of the oxygen redox mechanism.
Yeah.
Yeah.
Thank you, Professor Mukhopadhyay. So the last question is, so the participant is asking about how to characterize P2 and O3 coordination environments in these layered oxides.
Yeah, so the basic characterization is XRD. They're using
Yeah.
normal lab scale XRD can tell whether it's an octahedral coordination or a prismatic coordination. So it will tell the structure. For now, for just in case one wants to check the superlattice ordering, one can go with synchrotron XRD or neutron diffraction, and that can help in a better way. Yeah, so it depends on what exactly one wants to know. But overall, when it comes to the structure, the diffraction are the best things to bank on.
Yeah. Yeah. Thank you, Professor Mukhopadhyay. So if you could share any closing remarks to our audience, or maybe to early career researchers who might be interested in working on sodium-ion batteries.
Sure. So first of all, the thanks for the enthusiasm and thanks for the questions. I'm sorry not all questions could be taken. I'm really sorry about that. But yeah, thanks for attending and for all the questions and encouraging the discussion. And so all I wanted to say is that, as I mentioned in the beginning, that if lithium-ion battery is the king of electrochemical energy storage, I can say sodium-ion battery is the crown prince. But for it to become the king, that is what the target should be. A lot more work needs to be done on both sides, the cathode side as well as anode side. So as I also mentioned by responding to one of the questions, that when it comes to the cathode side and when we want to enhance the capacity, that is the energy density, the capacity and the voltage, one needs to work on the oxygen redox, which thankfully for the sodium-ion cathodes have been found to be a little more stable and reliable as compared to the lithium transition metal oxides, but a lot more work needs to be done. So that is an important area of research. Second, how to try and increase the capacity of the polyanion based cathode materials, moving ahead from sodium vanadium phosphate and trying to replace vanadium. Third, the anode side. Hard carbon is good. It is, I mean, with respect to the performance, good means it's okay, but the problem is that it is very difficult to control, because we know the structure of graphitic carbon very well, but hard carbon is something which does not have a well-defined structure. It will depend on the precursor, depend on the heat treatment condition. So controlling the electrochemical parameters to prevent sodium plating, minimize irreversible sodium loss can be a big challenge. So it is a good idea to do away with the hard carbon and work on alternative anodes. So that's another area when it comes to the materials and electrochemistry of sodium ion cells. So with this, I think I can close my closing remarks, and once again thank the audience for being so wonderful and for asking a lot of interesting questions.
Thank you so much, Professor Mukhopadhyay, for again answering to so many questions. Yeah, thank you so much for your time. Aparna.
This brings us to the end of today's session. We hope you enjoyed the broadcast, and we invite you to view the edited recordings from the past events in the ACS Science Talks library. At the end of session, you will receive, after the session, you will receive the certificates and the survey link. Kindly share your feedback with us so that we can continue to improve and serve you better. Till then, stay safe and healthy, and thank you everyone for joining us.
Thank you very much for having me today. Thank you.
Thank you. Thank you.